Hey everybody, Mr. Judson here. So we're still working on this idea of optimization, where we try to minimize or maximize something. And again, like I told you guys, these problems are never the same. They're always a little bit different. And so we just need to look at as many different types of problems as we can and try to figure this stuff out. So what this one says is that we want to find the point on this upside down parabola that has a minimum distance from 0, 2. So we're trying to minimize the distance. All right, that's what we want to take the derivative of, is the distance. Whatever it is you're trying to maximize or minimize, that's the thing I'm going to take the derivative of. Okay? Now, you look at this and you go, okay, great, but I'm taking the derivative of what? If I'm not sure what to do, I've got to at least start with a picture. Don't ever start a problem and then quit before you've drawn a picture and labeled everything. Because if we have something to look at, that may generate some thoughts that will help us out a little bit. All right? So let me get a graph. And I'm going to graph this upside down parabola, right? We know that x squared is a parabola. It's been flipped upside down. This 4 probably should be written over here, and then it's moved up 4 units. So this parabola is going to look like this. There's my vertex. If I go over 1, 1 squared is 1. If I go over 2, 2 squared is 4. So I've got points here, and there's my parabola. Okay? And what I'm trying to do is I'm trying to find a point on the parabola where I minimize the distance from 0, 2. Well, let's see, 0, 2 is right here. So if I want to minimize the distance, I've got a line segment that goes out, and there's another point on the parabola. Okay? Now, this point I can move around on the parabola. So what I need to do is I need to call it x, y, because I don't really know where it's at yet. Okay? I don't know those coordinates. This point right here, I know is at 0, 2. That's not going anywhere. Now I know if I move this point down here, my segment's getting longer. If I move it up here, at some point it gets kind of probably as short as it's going to get, but then it starts to grow a little bit, comes around, gets short again, and then starts getting longer for forever. Okay, so there's probably 2 answers to this, 1 point on each side. So what I want to do is I want to say that the distance between these points, this is our distance formula, it equals the square root of x2 minus x1 squared, so that would just be x squared, and then y2 minus y1, so plus y minus 2, and square that. And I'm trying to minimize the distance. All right? Now, it would sure be nice if there was only one variable over here. God, I sure wish I had an equation somewhere that told me what y is equal to. Right? This one right here. So we can use that. We could take this stuff right here and substitute it in place of y, and then what I have is an equation that has just x's in it. And so I can at least figure out the x coordinate of that point. All right, so let's see, I've got d equals the square root of x squared plus, I'm going to put 4 minus x squared in there for y, minus 2, and I still have to square that. Okay, now remember the square root of this is not just x and one of these. Doesn't work that way. Right? We got to multiply all this stuff out, add up my like terms, and so on. So let's see, I've got x squared plus 4 minus 2, that's 2, minus x squared, and I got to square that, still have the square root. If I square this thing, I get x squared plus, square the first term, multiply the 2 and double it, so that'd be a negative 2x squared. Double it, you get a negative 4x squared. And then you square the last term, you get plus x to the 4th. So now what I have is x to the 4th. I'm going to put this in parentheses and raise it to the 1/2. Okay? So x to the 4th. If I add these two together, I get negative 3x squared and then plus 4. There's my function for the distance. And so now to minimize it, we have to take the derivative, set it equal to 0, and solve. You guys take it from there. All right, so d prime, there are no dx's and dy's and d thetas, you know. What I'm trying to minimize, I've got it by itself. Just like saying, if I can get y by itself, I just take the derivative the normal way. So I'll bring the exponent down in front. Same thing on the inside. X to the 4th minus 3x squared plus 4. Subtract 1 from the exponent. Times the derivative of the inside. So times 4x cubed minus 6x. And so now I need to take that derivative and set it equal to 0 and solve. So let's see, whoops. So d prime, there's my fraction bar. I've got a 2 in the denominator. I've got to drop this down below and make the exponent positive. And this is what I have in the numerator. So I guess the good thing about this is if I want to set this equal to 0 and solve, the only way a fraction can equal 0 is if the numerator equals 0, right? It's the only way. So, you know, if I was setting this equal to 0, I'd just say move all this stuff over and multiply, and it'd be gone. So I've got 4x cubed minus 6x equals 0. I'll go ahead and factor that. Oh, come on. So let's see, I'll factor out a 2x, and so I'm left with 2x squared minus 3 equals 0, which to us means that either x equals 0, or, you know, what would it take for this to equal 0? Well, let's see, positive 3 over 2, so x squared would equal 3/2, and then x would have to equal plus or minus the square root of 3/2, which, what is that? Root 3 over root 2. And I'll multiply top and bottom by root 2. And so what I get is x equals plus or minus, this times root 2 is the square root of 6. This times root 2 is 2. Okay? All right, so there's my 3 places where the derivative equals 0. It means that's where a maximum or minimum could occur. And now I'm looking at this and I'm thinking, I don't want to take the second derivative of that to see where it's concave up and concave down. Oh my gosh. How are we going to do this? I'll tell you what, I'm going to make this easy on you guys. I'm going to make this really easy. I'm going to allow you to do the second derivative so that we can check to see if it's concave up or concave down on your calculator. Okay? When these equations get messy, our goal is not to make this the messiest problem we've ever seen. Our goal is to understand the calculus end of it. All right? So all we want to do is we want to get the second derivative and just check to see. I've got 3 numbers here to test. I'm trying to minimize the distance, which concave up is where a minimum occurs, and I just want to be able to check that. All right? So I'm going to grab my TI-89, and I'm going to get the second derivative. So let's see, let's turn it on first. Get back to my home screen. And I want to find the derivative of, I got to put this inside parentheses. So in parentheses, I've got 4x raised to the third minus 6x, close parenthesis, and then divided by, in parentheses, I've got 2 times the square root of x to the fourth minus 3x squared plus 4. And let's see, close parenthesis for the square root, close parenthesis for the denominator. And I want the derivative with respect to x. Oh my, that is ugly. All right, so the derivative of this is what I have written here, right? So there's my derivative. That is really ugly, but we're going to make this easy, okay? I just want to know, am I concave up or am I concave down? All right, so let's start with 0. D double prime at 0, and I'm not even going to write down what that second derivative is, okay? I just want to know, is it greater than or less than 0, so that I know if I'm concave up or concave down. Is my second derivative positive or negative at 0? Okay, so let's go back to the calculator. I'm going to clear this. I'm going to go, let's take 0 and store that in x. There it is. Okay, clear that. Now I want to know what this thing right here is equal to. So I hit enter to put it in my edit line, and then I hit enter to figure out what that is. So because 0 is stored in x, it found what this whole thing is equal to, a negative 3/2. So this is less than 0. Okay, my second derivative is negative, which means we are concave down. Is that what I'm looking for if I want a relative minimum? No. All right, so my phone rang, I had to go answer it. When I came back, this whole thing froze, and then it just went black. So I had to dump it and start over. So all I've done is I've just written down, here's the first derivative, here's the second derivative, there's what we got when we set it equal to 0 and solved. And I had just tested the second derivative at 0 and found it was concave down. Okay? Now remember, when we say concave down, we're not talking about this function. We're trying to minimize the distance. So it's the distance function that is concave down. I don't have a graph of that. We're looking for the distance between this point and some point along this parabola. And so if I was to graph that distance formula, it would be concave down at 0, which means there's a relative maximum. Now I can go back and look at this and say, you know, if I have a point right here, you know, picture a line segment that represents the distance. As I move it up, that distance is getting shorter, 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 shortest, longer, 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 longest, shorter, shorter, shorter. So what I have is if I'm concave down, it means I have a relative maximum at x equals 0. That means the distance straight up and down, relative to that area, this area right up in here, is going to be a maximum. Okay? Now I know there's other distances that will be longer. They'll be when that point gets down in this area, it'll just get infinitely long. But I'm going to have a minimum distance somewhere around here, then a maximum distance, then another minimum, and then it'll just get longer forever. Okay? Let me check my second derivative at positive root 6 over 2. So I want to plug that back into my second derivative to see if I get a positive or negative, and am I concave up or concave down. So I'm going to go back to my graphing calculator. Clear this off. I'm going to say let's take the square root of 6 divided by 2, and let's store that in x. Now I want to make sure, remember, I'm storing values in x, so I need to go back and clear those out when I'm done with this. All right? And so now I need to get my second derivative and evaluate it. So there it is. Put that in my edit line, hit enter, and there's what I get, a positive number. I don't care how messy the number is, it's positive. All right? So this was greater than 0, which means we are concave up. And if we're concave up, that's where a relative minimum occurs. Okay, remember, not concave up here, but in my distance formula. I'd go back and show it to you, but I lost it when this thing froze. Okay? But look back in your notes. D equals the square root of, we had some stuff there that we took the derivative of to get to this. And then if I do the second derivative at negative root 6 over 2, I think what I'm going to find is the same thing. So let me clear this. I'm going to arrow back up. Get that right there. This time, second, I want to insert a negative sign there. So I'll put that in for x. Clear that. I'll go back up here and get that. And still a positive number. So we are still concave up. Which is what I thought. I thought there would be, let's see, greater than 0. I thought there would be 2 points where we minimize the distance from 0, 2 to a point on the parabola. One right here, the other over here. Okay? And so that would be at square root 6 over 2 would be the x value for this point. Negative root 6 over 2 would be the x value over here. Okay? And I don't have the y value here. I don't even know what this question asked. Find the point on the parabola that has a minimum distance. Have I found the point yet? No, I haven't. So I need to go back and do that. So I think these 2 points are going to have the same y value. So I think if I went back and plugged it into the original parabola, I should be able to get both of those. Okay? So the original parabola was y equals 4 minus x squared. I'm now looking for the y coordinate. So whether I put positive or negative in here, I'm going to square it. So I'll get the same thing. So y is going to equal 4 minus, let's see, if I square that, I get 6 over 4, which is 3 halves. And 4 minus 3 halves, that's going to be 2.5. Or if you want to, we can call it 5 halves. So the distance is minimized at the points plus or minus root 6 over 2, comma, 5 halves. There's my final answer. All right, let's try another one. All right, here's a realistic problem. I think this happens all the time. A rancher has 200 feet of fencing and wants to enclose 2 adjacent corrals. What dimensions would maximize the area of those 2 corrals? Okay, I can just see the cowboys sitting out there in the dirt doing some calculus trying to figure out where exactly should we put the corners to maximize the area. I'm sure that happens all the time. So a rancher has 200 feet of fencing. That means if you add up all the fencing, all the sides, even the one in the middle, because you're going to have 2 corrals that are adjacent to each other, all the fencing material has to add up to 200 feet. Okay? So again, we should never stop until we've at least drawn a picture and labeled everything and really know what we're talking about. So I read this, and what I see is 2 adjacent corrals. There they are. I got to call them something, so I'll call this x, and if that's x, so is this. I'm guessing the 2 corrals would be the same size, so this would also be x and x, and this would be y, and this would be y, and this would be y, because those 3 sides are all the same. And all I know right now is these all add up to 200. So 1, 2, 3, 4x plus 3y, and that equals 200. So a lot of times, when we set up problems like this, we talk about a primary equation and a secondary equation. Your primary equation is the one that you want to take the derivative of. That's what I'm trying to maximize or minimize. The secondary equation is just an equation to help me get the primary one in terms of one variable. Okay, so the previous one, we had our parabola. That's not what we took the derivative of. We had a distance formula, and we used the parabola to substitute in and get everything in terms of x. Okay, so the parabola was the secondary equation. All right, so what I want to maximize is the area, and I'll just take the area of one corral. So area equals x times y. Now, if somebody said, well, what about the area of the whole thing? I'm going to go 2x times y. It ends up giving you the same answer. So it really doesn't matter which way you think about that. Okay? All right, so I want this to be in terms of one variable, so I'm going to solve for y and substitute in. So we'll say that 3y equals 200 minus 4x, and then divide by 3. We get 200 minus 4x over 3. And we're going to take that and substitute it in right there. So the area equals x times 200 minus 4x over 3. And now I need to take the derivative, set it equal to 0, and solve. Okay? So I probably should have paused in here somewhere and let you guys try to set this up. I guess I got excited. It's a great math problem. So let me have you guys take it from there and see if you can finish this. Okay? We're trying to maximize the area. All right, so I think the easiest way to take the derivative of this is really first just to multiply the whole thing out. So I'm going to write it this way. Area equals, I'm going to call this 200 thirds times x. And then I've got a negative 4 thirds times x. Upside down parabola. All right, we already know what we're looking for. We're looking for the vertex. So now I'll take the derivative, and what I'm going to get is 200 thirds. If I bring this down and multiply, I get a negative 8 thirds. Subtract 1 from the exponent. There's what I get, and I want to set it equal to 0 and solve. So let's see, if this was equal to 0, I would move this to the other side. So I'd have 8 thirds x over here, 200 thirds over here. I'd probably multiply both sides by 3. Times 3, times 3, those will cancel, those will cancel. So now what I have is 8x equals 200. Sounds like 8 quarters, right? So x equals 25. And so now I just need to verify, is that a maximum or a minimum? So I need my second derivative. So a double prime, I don't need a calculator for this. Derivative that's 0, derivative of this is a negative 8 thirds. And this is always concave down. So if we're concave down at 25, it means that's where there's a relative maximum. Remember, at x equals 25, our first derivative equals 0. That gives me the horizontal tangent. Now I just need to know, is the function concave down or concave up? Okay, and we're concave down, which means we have a maximum at x equals 25. Okay, so that's not my answer. Remember, the question was, what would the dimensions of the corral be? Okay, what dimensions would maximize the area? All right, so I know x is 25. What's y going to equal? Well, let's go right here. If I plug in a 25, so y at 25 is going to equal 200 minus 4 times 25, that's 100, over 3. So I got 100 over 3 which is 33 1/3. So the dimensions are 25 feet by 33 1/3 feet. There we go. All right, we got one last problem here to try. So it says a document contains 32 square inches of print. Okay, that's all the writing that's on there, 32 square inches. And must have a 2-inch border around it. Maybe it's some official document that someone's going to put in a frame and these are the requirements. I don't know. Okay. What dimensions would minimize the sheet of paper being used? In other words, I want to get my 32 square inches of print in there. I want to have my 2-inch border, but I want to minimize the size of the sheet of paper. I don't want it to be a huge picture. All right? So you guys draw a picture of this and see what you can come up with. Remember I told you, every problem's different, right? Every one of them's a little bit different. So here's my sheet of paper. And let's just say that here's my 2-inch border. And I've got all this writing, whatever it is, inside here. Okay? And what I'm trying to do is I'm trying to minimize the size of the sheet of paper. Well, one thing I know, if I say that this is x and this is y, these two lengths, I know that x times y would give me 32 square inches. Right? 32 square inches of print. So that's the first thing I know. X, y equals 32. So think to yourself real quick, primary equation or secondary equation? It's got to be secondary, right? I'm not taking the derivative of this, I'm trying to minimize the area of that sheet of paper, of this whole thing. All right, so we know that the dimensions here are going to be 2 inches, 2 inches, 2 inches, and 2 inches. So the length of this side is going to be x plus 4, right? And the length of this side, let me do it over here, is going to be y plus 4. Those are the dimensions of the entire piece of paper. That's the part that I'm trying to minimize. So area equals length times width, so x plus 4 times y plus 4. But it'd be really nice to have this in terms of just one variable, right? So if I say y equals 32 over x, and I take that and substitute it right there, I should be good to go. Area equals x plus 4 times 32 over x plus 4. And now I should be able to take the derivative, set it equal to 0, and solve. You guys see if you can finish that up. All right, so I think it would be helpful to go ahead and multiply this out. It'll probably make the derivative a little bit easier. So a equals, if I multiply by x, I just get 32 plus 4x plus, what is that, 128 over x plus 16. And so that means that the area equals, if I add these, I get 48 plus 4x plus 128x to the negative 1. And now I'll take the derivative. The derivative of this is going to be 0. Derivative of this would be 4. Here I'll get a negative 128x to the negative 2. Okay, so now I want to set that equal to 0. So I've got 4 minus 128 over x squared equals 0. I'll move that to the other side of the equal sign so that it becomes positive. I'll then bring the x squared back over here. So I've got 4x squared equals 128, and I'll divide by 4. So that'll become 32. And now I take the square root of that, and I get x equals plus or minus the square root of 32, which would be 16 times 2, that's 4 root 2. So does the negative number make sense in this situation? X was, let's go back to our picture. X is this distance right here. Could that be a negative distance? No, it can't. Okay, so I'm going to throw out the negative and say we really just want the positive answer. All right, so what should the dimensions of the piece of paper be? What dimensions would minimize the sheet of paper? The whole sheet. So if I've got 4 root 2, then I'm going to say that this length right here would be 4 root 2 plus 4. And what's my y value? My y value is going to be 32 divided by 4 root 2. Which if I rationalize it, well, first of all, let's do 32 divided by 4, that's 8 root 2. And then if I call that 8 root 2 over 2, I get 4 root 2. Oh, look at that. Plus 4. So 4 root 2 plus 4. My sheet of paper is a square, right? That's the best situation if I want to minimize the amount of paper that I'm going to use. So we're going to say here that the paper should be 4 root 2 plus 4 inches by 4 root 2 plus 4 inches. There's my dimensions for that piece of paper. Optimization, trying to maximize or minimize something. You know, how do you know when it's an optimization problem versus maybe a related rates problem? Well, related rates, they're going to ask you at what rate is something changing, and here they're going to ask questions like, what should the dimensions be to minimize or maximize something? So you got to make sure we recognize the way they're asking the questions and then know what to do. All right, you guys, that's what we have for today. Let me get you a homework assignment. All right, so we're on week 16. This is our Wednesday piece, page 223. We're going to do 19, 22, 25, and 39. All right, you guys, that's it. You guys take care, stay safe. I will see you later.